So in the following theorem, we will construct a Lebesgue still-just measure on R out from a non-decreasing and a continuous function from the right. So let us denote by F, function from R to R, to be a non-decreasing and continuous from the right. Then there exists a unique Lebesgue still-just measure, let's say mu sub f, defined on the Borel sets in R, such that we have the following property. So the measure of the half-open, half-closed interval xy is the difference of the function values at the endpoints. So for all x less than or equal to y. So the proof of this is somewhat similar to the construction of the Han-Kolmogorov extension. And I will leave the details for you to read in the course notes. So the proof was provided in the course notes. So those who are interested, you will see that the construction of this measure mu sub f is similar to the construction of the one-dimensional Lebesgue measure. And in fact, if you have the identity function, so I, let's say from R to R, given by this identity function. So this would be y minus x. And this is basically the elementary content in R. Hence, you will have the one-dimensional Lebesgue measure. So mu sub I would be your 1D Lebesgue measure. To be precise, it's the 1D Lebesgue Borel measure. Okay, since take note that f is non-decreasing, so therefore this is positive. Is non-decreasing. Okay, so that's how you construct, in fact, the measure mu sub f. You start with this definition on the cells. This will be a content on the semi-ring consisting of these one-dimensional cells, and then you follow the construction of the one-dimensional Lebesgue measure. Let us state some remarks. So if you have, let's say, two non-decreasing and continuous functions from the right, then the corresponding Lebesgue still-just measures are equal if and only if these two functions differ by a constant c. So for some c in R. Well, to prove this, so let us look at this direction. So suppose the two measures are the same, mu sub f equal to mu sub g, then from the definition or from this property, okay, this implies that f of x minus f of y is equal to g of x minus g of y, and this is true for any pair of real numbers x and y. So if you take, let's say, y to be 0 and x arbitrary, then rearranging these terms, so we have the following equations. F of x is equal to g of x plus f of 0 minus g of 0. Take note that these are constants, so we can let this to be our c. And this is true for any x, therefore we conclude that f is equal to g plus this constant c. For the other direction, well, this follows from the fact that if I take the measure of this cell xy, this is equal to what? F of y minus f of x, and this difference is equal to, since f is equal to g plus c, so f of y is equal to g of y plus c minus the quantity g of x plus c, and you can see that c will cancel, and you will have the difference g of y minus g of x, and this is the same as mu of g of this cell. So if you apply uniqueness, since there's a unique Lebesgue-Stieltjes measure that will satisfy these properties, then we conclude that mu f must be the same as mu g on the Borel sets. Okay, so if two non-decreasing and continuous functions from the right are equal, the corresponding measures are equal, then this is true if and only if the functions f and g differ by a constant. Okay, for the next remark, take note that given a measure mu, one can define the corresponding distribution function. So this is the distribution function associated with mu. It is, take note that it is non-decreasing and continuous from the right. So we can take this as our f, our function f in the previous theorem. Now, if we take the measure corresponding to this non-decreasing and continuous function from the right, what would be the measure? Well, you end up with the original measure. Well, to see this, take note that, again, it is enough to show that these two are equal on these cells, okay? X less than y. According to the previous theorem, where f is the distribution function, this should be d mu y minus d mu x. And we have established in the previous lecture that is the difference of these two distribution values is the same as the measure of xy under mu. Okay, and again by uniqueness, this implies that we have this equality of measures in the Borel sets in R. So that should be replaced by BR as well. Okay, so constructing the measure from the distribution function with a given measure, you end up with the original measure. Okay, so now we would like to establish sufficient conditions for regularity of Borel measures. And let us restrict the study for metric spaces. So let us suppose that X is a metric space. And suppose that there exists a sequence of open sets, let's say Q sub k, with the following properties. So the closure of this open set is closed, but we need that it is also compact. So this is true for any positive integer k. The closure of U sub k is contained in the next open set, and U sub k increases to x as k goes to infinity. Now, let us start with a Borel measure. So this means that the measure of compact subsets of X are finite. Then, for each Borel set A in X, one can find an open set O and a closed set, say C, such that C is contained in A, and A is a subset of O, and we also need a positive epsilon. Okay, and a positive epsilon. Then we also have that the measure of the difference between the open set and the closed set is less than epsilon. Furthermore, one can show that mu is regular. So you have a metric space wherein you can write the metric space as an increasing union of open sets, wherein the closure of the open sets are compact, and these are contained in the next open set UK plus 1. I will not give the proof here. Again, you can look the proof in the course notes. Well, the idea here is to establish first that this is true in the case of finite measure space. Okay. And then extend that to the general case using this covering of X, the open sets U sub k. Well, note that X being the metric space, the Euclidean space Rn satisfies the above condition. By taking the U sub case to be the open ball centered at the origin with radius k. So this is the set of all points in Rn with distance from the origin. So that's the Euclidean norm being less than k. And you can see that if you take the closure, this will be compact because you will have the closed and bounded ball. And the closure would be a subset of the ball centered at 0 with radius k plus 1. And if you increase the radius, you end up with the whole space Rn. Okay, so as an illustration, let's say you have this ball here. And oops, so this would be, let's say, having, so this is the center O, the radius is k, and here the radius is k plus 1. So you have an increasing sequence of balls wherein the closure of the previous one is a subset of the next one. Okay. Let us move this here. So these conditions are satisfied by the Euclidean space. Okay, the Lebesgue measure is also a Borel measure. Well, to see this, indeed, if I have, let's say, a compact set K in Rn, then it is bounded. Hence, K must be a subset of some ball for some radius R. Okay. And then, in this case, the measure of this compact set, the Lebesgue-Borel measure by monotonicity is the Lebesgue measure of this ball, and we will see, well, one can see that this ball has a finite Lebesgue measure. In fact, you can say that this is what a subset of this set as well. So this is less than or equal to, okay, if you take the Lebesgue measure of this n-dimensional and let us make the other set open. So this is the cell, and we know how to compute the Lebesgue measure. This is the same as the elementary content. So this is equal to 2r. That's the side length. And since the side lengths are all equal, the elementary content would be 2r raised to n. So if n is equal to 1, you end up with the length of the interval. If n is equal to 2, you end up with the area of the square. And this is, of course, finite. So the Lebesgue measure, the Lebesgue-Borel measure is indeed a Borel measure. And from this, it follows that, so the conclusion of the previous theorem, conclusions of the previous theorem hold for x equal to the Euclidean space and mu the n-dimensional Lebesgue-Borel measure. So in particular, the Lebesgue-Borel measure is regular. Moving further, in fact, one can prove a more better or a better result. So consider, let's say, the assumptions of the previous theorem. So in other words, let us highlight that one. So this is the one that we are referring to. So X a metric space, and we have this collection of open covering of X satisfying these three properties. Okay. So those are the assumptions. Then for every Borel set in X, there exists, let's say, a set G, which is a countable intersection of open sets. So that is in tau delta, where tau is the metric topology on X. So this is sometimes called a G delta set. And there exists as well a set F, which is the countable union of closed sets. So that is an element in tau C sigma, which is commonly called an F delta set. So again, a G delta set is nothing but a countable intersection of open sets, while an F sigma set is the countable union of closed sets. Such that this F is contained in A and A is contained in G. And the measure of the difference, let's see, of the G delta set and F sigma set is the same as the measure of A minus F. This is the measure of G minus A, and these are all 0. So that as an illustration here, we have an F that is a subset of A, and A is a subset of G. And to visualize, let's say, the set differences, let us think of the area. And the difference would consist, let's say, at least in this illustration, a finite number of points. And this blue region here would be G minus A. The red one would be A minus F, and G minus F would simply be the union of these two. So let's say you can think of the measure as the Lebesgue measure. So if the difference, let's say, consists of a finite number of points, then the Lebesgue measure would be 0. Okay. So we have this illustration here for this theorem. So let us look at the proof. For each, let's say, n positive integer, going back to the previous theorem here, if you take epsilon to be 1 over n, okay, and then it is possible to have an open set, let's say On, and closed set Cn, such that C sub n is a subset of A, and A is a subset of O sub n, and that the measure of the difference of the open set and the closed set is less than 1 over n. So the natural candidate for the F sigma set would be the countable union of the C sub n's. Since C sub n is contained in A, then F is also a subset of A. And the natural candidate for G is also the intersection of these open sets O sub n. Since O sub n contains A or any n, then the intersection is also contains A. So we now have so this is an element of T tau sigma. So that's an F sigma set. And this is now an element of tau delta. So a G delta set, that is the intersection of closed sets. Okay. Also, take note that G minus A is a subset of On minus A. Since G is the intersection of the O sub n, so G is a subset of O sub n. And then you subtract both sides. And this is a subset of O sub n minus, so looking back at this property, so if we subtract a smaller set, in particular C sub n, then we have a larger set. So that would be this one. And in a similar manner, A minus F, since F is the whole union, then this is smaller than the set difference A minus F sub n. So take note that F is larger than any C sub n. So I should say C sub n. Since A is a subset of O sub n, so this is also a subset of O sub n minus C sub n. So therefore, if we apply the monotonicity of the measure, the measure is always non-negative. So this is less than or equal to the measure of O sub n minus C sub n, but according to the construction, this is less than 1 over n. And similarly, for the second case, you also have this inequality. So therefore, if we let n tend to infinity, we will get the measure of these two is equal to 0. So going back to the figure, so that's the blue part and the red part. And applying, let's say, the sub-additivity of the measure, this implies also that, or let's say by additivity, this also implies that the difference g minus f has measure 0. And we have established the properties desired by the theorem. So here is your subset or subsets. And for this part, you have g minus f, a minus f, g minus a. And you can check that these are the three parts. Okay, so that's the proof of the theorem. So just I would like to mention the terminology here. Why is it called a G delta and F sigma? So we know the subscripts already. So G delta, so G here represents for the German words Gebiet, and delta, of course, is Durchschnitt. Which translate to, let's say, area. So you can think, let's say, as an open area, and a Durchschnitt is again average. So you can think of the common element. And for F sigma, so F here refers to firm, and sigma, let's say for sum. So this is what? Well, according to Google Translate, this is sum. So you can take of this as a union, and firm is literally translates to closed. Okay. So average area, you can think of this as a common open area, and then sum of closed, so you can think of this as the union of closed sets. Because basically, if let's say if you want to take quote unquote the sum of sets, you combine or you take the union of those sets. So that's the explanation why they're called G delta, so and F sigma sets. So going back again to this theorem, this tells us that, okay, Borel set, well, except on a set of measure 0, because these sets highlighted here in blue and red have measures that are equal to 0, then a Borel set is almost a F sigma set or a G delta set. So writing that more precisely, so in let's say Rn, so let us now specialize in Rn. Applying that previous theorem, then a Borel set is a G delta set, or let's say an F sigma set. So what is a G delta set again? So this is countable intersection of closed sets And the other one is the countable union of open sets. Well, they are equal up to a Lebesgue null set. Well, you can also say that a Lebesgue-Borel null set. Because here we take the Lebesgue-Borel measure. So those are Borel sets. How do they look like? They are, well, either a countable intersection of closed sets combined with a Lebesgue-Borel null set, or a countable union of open sets combined with another, probably or possibly another Lebesgue-Borel null set. So this simplifies, let's say, at least the characterization of Borel sets up to a set of measure 0. And since we know before that a Lebesgue measurable set in Rn is a Borel set except on a set of measure 0, this implies that a Lebesgue measurable set can be also written as a G delta set or an F sigma set plus some Lebesgue null set. Here we use the fact that a Lebesgue-Borel null set is also a Lebesgue null set, since the Lebesgue-Borel measure and the Lebesgue measure coincides on the Borel sets. So another simplification of how do Lebesgue measurable sets look like. So a set is Lebesgue measurable if and only if you can write it as a union of a G delta set and a Lebesgue null set. And you can also write it as the union of an F sigma set with a Lebesgue null set. So again, similar to Borel sets, a Lebesgue measurable set is almost a countable intersection of closed sets and almost a countable union of open sets. By almost, we mean precisely that they differ only on a set having a Lebesgue measure 0. And that's it for Borel measures. We will talk about image measures in the next lecture.